Welcome to Homework Lib.
For this problem on the topic of kinematics of particles, we are told that a race car labeled A is traveling on a straight portion of a racetrack, while a second race car B is traveling on a circular portion of the same track. Now, we know the speed of A is increasing at a given rate, so we know its acceleration. We also know the deceleration of B at the same position. We want to determine the velocity of B relative to A at that position and the acceleration of B relative to A. So we'll first write down the speeds of both cars. So the speed of car A, VA, is equal to 240 kilometers per hour. So in SI units, this is 66.67 meters per second. The speed of B is 200 kilometers per hour. And this is 55.56 meters per second. Their velocities are as follows. For A, we have 66.67 meters per second, and that's to the left. The velocity of B is 55.56 meters per second at an angle of 50 degrees below the negative x-axis. So now we can calculate the relative velocities. Now the relative velocity of B to A is the velocity of B minus the velocity of A. And so this is equal to 55.56 times the cosine of 50 degrees. So we're breaking the velocity of B into its horizontal and vertical components. That's to the left, plus 55.56 times the sine of 50 degrees, and that's vertically downward, plus the velocity of A, which is 66.67, and that's to the right. So the positive sign is because it's a minus in the opposite direction. And so calculating in components, we get this to be 30.96 to the right, plus 42.56 downward. So if we resolve this into a single vector, we get the velocity of B relative to A to be 52.63 meters per second, and the angle is 53.96 degrees below the positive x-axis. And so we can write this in the same units as given in the problem as 189.5 kilometers per hour, and we can round the angle to 54 degrees. So there we have the velocity of B relative to A. Now, before we find the acceleration of B relative to A, we need to find the tangential and normal accelerations. Now we know the acceleration of A as a tangential component. We'll mark it with subscript t, and this is equal to 10 meters per square second to the left. The tangential acceleration of car B is equal to 6 meters per square second at an angle of 50 degrees. The normal accelerations, we know AN is equal to the speed of the car squared, v squared, over the radius of the circular motion, which is rho. Now, for car A, rho is infinity, so its normal acceleration its normal component of the acceleration, an, must equal to 0. But for car B, we do have the normal component of acceleration. And this is equal to 55.56 squared over the radius of that portion of the track, which is 300, which gives us the normal component of acceleration to be 10.288 meters per square second, and this is at an angle of 40 degrees below the positive x-axis. So now we have the normal acceleration, and we can find the acceleration of B relative to A. So the acceleration of B relative to A, B slash A, is equal to the acceleration of B minus the acceleration of A. And this is equal to the tangential component of the acceleration of B plus the normal component of the acceleration of B minus the tangential component of the acceleration of A minus the normal component of the acceleration of A. So the total acceleration is the sum of the tangential and normal components. And so if we put our values into this, this becomes 6 at an angle of 50 degrees plus 10.288 at an angle of minus 40 degrees plus 10 to the right plus 0. The normal component of the acceleration of A is 0. And so if we put this into numbers, we get this to be 6 times the cosine of 50 degrees plus 10.288 times the cosine of 40 degrees plus 10 to the right. So we breaking these up into horizontal and vertical components, plus 6 sine of 50 degrees minus 10.288 sine of 40 degrees. And so calculating, we get the acceleration of B relative to A to be, so we'll resolve these vectors and we get 21.8 meters per square second at an angle of 5.3 degrees below the positive x-axis.